Hello everyone, welcome to you in this video lecture on degrees of freedom. This is lecture number 2 under the subject Theory of Mechanisms and Machines. This lecture is specially designed for the GATE aspirants of mechanical engineering and the students of mechanical engineering having 4-year semester course will also be benefited by this lecture. The contents of these lectures are degrees of freedom of planar mechanisms, redundant degrees of freedom, redundant kinematic pairs, redundant links, solution of numerical example, and at the end we'll solve gate problem. Degrees of freedom of a planar mechanism. What is the definition of degrees of freedom? The degrees of freedom of a planar mechanism is the minimum number of independent coordinates required to completely define the relative movements between its all links. So this is the minimum number of independent coordinates which can completely define the relative movements between its all links. Now let us note some important concepts on degrees of freedom of a planar mechanism. We all know that a mechanism must have one fixed link. A mechanism must have one fixed link. Second one, a free link has 3 degrees of freedom in planar motion. Let me explain this. This is a free link in plane motion. The link can translate along x direction, it can translate along y direction, and as well as it can rotate along z axis, that is the axis perpendicular to the plane of motion. So 3 independent coordinates can completely define the motion of the unconnected link. So a free or unconnected link has 3 degrees of freedom. What are the independent coordinates? That is delta x1, that is translation along x direction, delta y1, that is translation along y direction, and delta theta 1 is the rotation about z direction. The axis with z axis is the axis perpendicular to the plane of motion. Now let us come to the third point, that is a lower pair, that is revolute or prismatic, because in plane for planar mechanism lower pair means revolute pair or prismatic pair, reduces 2 degrees of freedom. Let me explain this also. Now this unconnected or free link has been connected to this fixed link by a revolute pair here. Now the link can only rotate about the axis perpendicular to the plane and passing through the revolute joints. So two motions has been restricted, that is translation along x direction and translation along y direction. Now only delta theta 1 is the independent coordinates that can completely specify the motion of this link. So degrees of freedom was 3 when it was unconnected. Now when it is connected to a fixed link by a revolute pair or lower pair, then degrees of freedom becomes 1. So 2 degrees of freedom has been reduced. Next point. A higher pair reduces 1 degree of freedom. Let me explain this. Now this unconnected or free link is connected to the fixed link by a higher pair. So the link can now slide along the fixed link and as well as it can rotate about this higher pair. So two independent coordinates are required to specify the motion of the rigid link. So the degrees of freedom now becomes 2. So degrees of freedom is reduced from 3 to 2. So the higher pair reduces 1 degree of freedom. So with this concept, let us develop a equation for a planar mechanism which contains n number of links and j number of lower pairs. The degrees of freedom of the mechanism which having n number of links and j number of lower pairs is f is the degrees of freedom equal to 3 into n minus 1 minus 2j. Let me explain this equation. If the rigid body have n number of links and the mechanism must have one fixed link, so how many unconnected links are there? N minus 1 unconnected or free links, and one link having 3 degrees of freedom. So n minus 1 number of unconnected links will have 3 into n minus 1 degrees of freedom, and one lower pair reduces 2 degrees of freedom. So j number of lower pairs will reduce 2j degrees of freedom. So total degrees of freedom will be 3 into n minus 1 minus 2j. This equation is known as Kurzweil equation. This is known as Kurzweil equation. If a mechanism has single degree of freedom for a single input, the mechanism is called a constraint mechanism. So when a mechanical mechanism has single degree of freedom for a single input, the mechanism is called a constraint mechanism. And this condition is given by Grubler's criteria. So the Grubler's criteria of constraint mechanism will be what? If I put f equal to 1, then the equation becomes 1 equal to 3n minus 3 minus 2j. So 3n minus 2j will be equal to 1, and this minus 3 comes here. So 1 plus 3 equal to 4. So the Grubler's criteria for constraint mechanism is 3n minus 2j equal to 4. A higher order lower pair connects more than 2 links. Now we are describing here a higher order lower pair. So what is higher order lower pair? The lower pair which connects more than 2 links. Here this is a higher order lower pair which connects link 2, link 3 and link 4. So this is called a second order higher pair because it joins 3 links. So which is equivalent to two simple link. Two simple link which connects, this simple link connects link 2 and 3, and this simple link, a simple pair connects link 3 and 4. So a second order higher pair is equivalent to two simple pair. So when a mechanism contains higher lower pairs, we can replace this higher pair by an equivalent number of simple pair. By the equation what? By the equation j is equal to total number of simple pair, which is equal to j1. j1 is number of simple pair plus 2j2. j2 is the number of second order higher pair. j3 is number of second order triple pair plus dot 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 ij. Now what is the significance of ji? Ji is number of higher order lower pair which connects I plus 1 number of links. So what is the significance of J1? J1 is the simple pair, simple lower pair. So it connects 1 plus 1, 2 links. This is a simple pair. Now J2 is second order lower pair. So J2 connects how many links? 2 plus 1, 3 number of links. Now J3 connects how many links? 3 plus 1, 4 links. So the equivalent number of simple pair is to be determined by this equation, where J is equal to J1 plus 2j2 plus 3j3 plus iji. Now we know a higher pair reduces 1 degree of freedom. Accordingly, a mechanism which contains h number of higher pair, the equation of degrees of freedom will be what? We can extend our equation by this, that is f equal to 3 into n minus 1 minus 2j minus h, because one higher pair reduces 1 degrees of freedom, so h number of higher pair will reduce h number of degrees of freedom. So the equation becomes f equal to 3 into n minus 1 minus 2j minus h. Redundant degrees of freedom. Redundant degrees of freedom exist when a link can be moved without transferring motion to the other links. Let me explain this. This is the mechanism, say mechanism A, in which the link 3 can slide without transferring motion to link 2 and link 3. So this degrees of freedom of link 3 is called redundant degrees of freedom. So if we apply the equation to find out the degrees of freedom of this mechanism, that becomes what? F equal to 3 into n minus 1 minus 2j minus h. So how many links are there? 1 is the fixed link, this is 2, this is 3 and this is 4. So 4 links, so 3 into 4 minus 1. How many lower pair is there? 1, 2, 2 revolute pair and 2 prismatic pair. So 4 lower pair, so 2 into 4, and there is no higher pair, so h becomes 0. So 3 into 4 minus 1, that is 9, minus 8 becomes 1. So degrees of freedom by the equation becomes 1. But at this configuration, link 2 and link 4 cannot be moved because they are permanently locked. At this situation, see here, link 2 cannot move because link 3 restrict their movement. So link 2 and link 4 cannot be moved at all. They are permanently locked. So at this situation, the mechanism becomes a structure. So degrees of freedom of this mechanism is 0. So our formula does not work perfectly. So what is the reason? The reason, there exists a redundant degrees of freedom of link 3. So what is this one? The formula gives the redundant degree of freedom of link 3. So this one is nothing but the redundant degree of freedom of link 3 along its length. Now consider another configuration. We have just modified this mechanism by bending the link 3 like this. Now link 3 cannot move without transferring motion to link 2 and 4. So in mechanism B, there do not exist any redundant degrees of freedom, and right now the link 2 and 4 can be moved and the mechanism have 1 degree of freedom. So here the formula works perfectly. So at this mechanism 3, link 3 cannot move without transmitting motion to link 2 or 4. So link 3 here cannot be moved without transferring motion to link 2 and link 4. No redundant degrees of freedom is present here and the formula will work perfectly. So this mechanism will have 1 degree of freedom. So from this concept of redundant degrees of freedom, we can modify our equation. Now the effective degrees of freedom of a mechanism will be what? F equal to 3 into n minus 1 minus 2j minus h minus fr, where fr is the number of redundant degrees of freedom. So right now in this, if I modify this equation by this and apply for this mechanism A, the mechanism degrees of freedom of mechanism A will be 0, because Fr is 1, so this one minus 1, that will be 0. Now let me explain redundant kinematic pairs. A mechanism may contain redundant kinematic pairs. So what is redundant kinematic pairs? Kinematic pairs which are not kinematically important, but they may be required due to some other considerations. The examples are hinges of door and shaft mounted on two bearings. Let me explain. Say a door is connected to the frame by 2 or 3 hinges. But one hinge can give the door same motion, same kinematics can be produced by a single hinge. So by counting, the hinges may be 3 or 2, but kinematically it is 1. So extra hinges becomes redundant. Say a door have 3 hinges connected with the frame. So frame is the fixed link and door is the one single links. So how many links? 2 links and 3 hinges. So what will be the degrees of freedom? 3 into 2 minus 1, that is 3, minus 2 into 3 if there is 3 hinges. If we apply the formula blindly, then it becomes 3 minus 6 minus 3. So degrees of freedom becomes minus 3, but it has 1 degree of freedom because the door can rotate. So the 2 hinges becomes redundant kinematic pair. Only kinematically there will be only 1 hinge. If 2 are redundant, then effective number of hinges is 1. So now 3 into 2 minus 1, that is 3, minus 2 into 1 is 1. Similarly, if a shaft is mounted on 2 bearings, one bearing can give the shaft same kinematic motion, so one becomes redundant. So this is the concept of redundant kinematic pair. Now let us come for this mechanism. Let us find the degrees of freedom of this mechanism by applying our formula. What is F? F equal to 3 into n minus 1 minus 2j minus h. So how many links are there? One is the fixed link. This is link number 2. This is link number 3. This is link number 4. This is link number 5. And this is link number 6. So 6 links are there. How many revolute pairs? 1, 2, 3, 4, 5. 5 revolute pair and 1, 2, 3 prismatic pair. So total number of lower pair 5 plus 3 is 8. So if we apply our formula here, then we will get 3 into 6 minus 1 minus 2 into 8 minus 0 because no higher pair is there. So the degrees of freedom becomes minus 1. This is 15 minus 16 becomes minus 1. This implies that the mechanism is statically indeterminate. The degrees of freedom negative, the significance of negative degrees of freedom is the structure is statically indeterminate. But practically the mechanism has 1 degree of freedom. So here also our formula do not work perfectly. What is the reason behind this? The reason behind this is the movement of links 5 and 6, determined by the prismatic pair P15 and P16. If 5 is connected to 1 by 15 and the axis of this prismatic pair is horizontal, then 5 is constrained to move only horizontal direction. 6 is also constant to move only in horizontal direction. So link 5 and 6, movements of link 5 and 6 are restricted by P15 and P16. And here one extra hinge is provided here, that is P56, that kinematically becomes unimportant. This has no importance in kinematics, because 5 and 6, motion of 5 and 6 are already restricted by P15 and P16. 6 can move only in the horizontal direction and 5 can move only in the horizontal direction because of these two prismatic pairs. So no need to provide this prismatic pair for kinematics. There may be some other consideration, maybe another force consideration. So the prismatic pair between 5 and 6 becomes redundant. And when this happens when three links are connected by three prismatic pairs. Here link 1, link 5 and link 6 are connected by P15, P16 and P56. Three prismatic pairs, and all the pairs are in same direction. So three prismatic pairs are in same direction. So by this concept we can now modify our formula of effective degree of freedom, and that becomes what? F equal to 3 into n minus 1 minus, we have modified here by redundant kinematics pair, 2 into j minus jr minus h minus fr. The new term is jr, and jr is the total number of redundant lower pairs. Total number of redundant lower pairs. Now, similar like redundant pairs, there may be redundant links in a mechanism. So let me explain this. What is redundant links? Say this is mechanism A. For mechanism A, the length of 2, 5 and 4 are equal. Let us find the degrees of freedom of mechanism A. What is the degrees of freedom? 3 into n minus 1 minus 2j minus h. So 3 into 5 minus 1, because there is 5 links, and 1, 2, 3, 4, 5, 6. 6 revolute pairs. So 2 into 6. So this is 12 and this is 12. So this becomes 0. But practically this mechanism can rotate. Link 2, link 5 and link 4 can rotate. So the degrees of freedom of this mechanism is 1. But the mechanism has a single degree of freedom. The reason for this mismatch is presence of redundant link. Which one is redundant? Link 5 or 4 is redundant because they have same function. The functions of link 5 and 4 are same. Hence, one of these links becomes redundant, and the mechanism is equivalent to this mechanism, having 4 links and 4 revolute pairs. Why this extra link is given? This extra link is given to avoid an uncertainty consideration that I will explain to you in the class of mobility. So from the concept of redundant links, we can modify our formula of effective degrees of freedom, and that becomes 3 into n minus nr, this is the new term, minus 1 minus 2 into j minus jr minus h minus fr, and nr is the total number of redundant links. So nr is the total number of redundant links. Now this we have already explained that for this mechanism the actual degree of freedom is 1, but by the formula we have predicted degree of freedom was 0. The mismatch is due to the redundant link number 5 or 4, because they have same function. So here exists one redundant link and our formula do not work perfectly. So here our formula not work perfectly. But if the link 4 and 5, length of link 4 or 5 are not same, then the redundancy vanishes and the formula works perfectly. For this mechanism, this is actually a structure, and both actual and predicted degrees of freedom is 0. So if intermediate link, that is link number 5, is dissimilar with links 2 and 4, then the redundancy vanishes and the theory works satisfactorily. So let us solve one numerical problem on degrees of freedom. Figure shows, two figures are shown, that is figure 1 and figure 2. Two mechanisms are shown. Determine the degrees of freedom of this mechanism. So let us start for mechanism 1. What is the degrees of freedom? So degrees, how many links are there? Fixed links are 1, denoted by 1. This is link 2, 3. The slider is 4. This is link 5. This is link 6. This is 7 and 8. So n equal to 8. N equal to 8. And how many revolute pairs are there? 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, 6, 7. And this is a higher order revolute pair or second higher order revolute pair. Why? Because this revolute pair R2 joins 3 links. Link 3, link 4 and link 5. So this is a higher order lower pair. So how many total number of lower pair? That is j equal to j1 plus 2j2. j1 is 8. We have already determined 1, 2, 3, 4, 5, 6, 7 and a prismatic pair. So 7 revolute pair, 1 prismatic pair. So 8 simple pairs and 1 second order higher pair. So 8 plus 2 into 1 is equal to 10. And there is 8 number of links and there is no higher pair, no higher kinematic pair. So what is the degrees of freedom? F equal to 3 into n minus 1 minus 2j minus h. So that becomes 3 into 8 minus 1, that is 21, minus 20 is 1. So degree of freedom of the mechanism A is 1. Now let us go for mechanism B. Now here the link 3, this is link 3, this disk is link 3, has a redundant degree of freedom because link 3 can rotate without transferring motion to link 2 and link 4. This can be rotated about this axis without transferring motion to link 4 and link 2. So here exists one redundant degrees of freedom. And how many links? 4 number of links. How many lower pair? 1, 2, 3, 3 revolute pair. And here one, here is one higher pair. So 3 link without transferring motion to the other links. So there is a redundant degree of freedom. So f becomes 3 into n minus 1 minus 2j minus h minus fr. So n is 4, j is 3, 3 revolute pair, 1 higher pair here between 2 disks. So minus 1 and 1 redundant degree of freedom. So minus 1. So 9 minus 6 minus 1 minus 1. So becomes 1. So this mechanism has also 1 degree of freedom. Now problem number 1 from GATE examination. The number of degrees of freedom of the planetary gear train shown in the figure has to be determined. So this is a planetary gear train. Number 1 is fixed link, 2 is the sun gear, 3 is the arm and 4 is the planet gear. So how many links? 4 links, 1, 2, 3, 4. And how many lower pair? This is a simple revolute pair. J1 is a simple revolute pair. H is the higher pair between 2 and 4 and J2 connects link 1, 2 and 3. So this is a second order higher pair. This is a second order higher pair. Now n equal to 4, h equal to 1 and j becomes how much? J is J1 plus 2J2. J1 is 1 and J2 is also 1. So 1 plus 2 into 1 is 3. So the degree of freedom of the planetary jet train is F equal to n 3 into n minus 1 minus 2J minus H. So 3 into 4 minus 1 minus 2 into 3 minus 1. So that is 9 minus 6 minus 1. So equal to 2. So the planetary gear train have 2 degrees of freedom. So we have completed our lecture. Thank you for watching this video. I wish you best of luck in your GATE examination. Jai Hind.